Hello everyone, my name is Adiola Banis and I'm a PhD candidate at Carnegie Mellon University. I'm pleased to present a work titled Bleep, Motor-Enabled Audio Side Channel for Constrained UAVs, which is a collaboration between me, Dr. Hae-Young No of Stanford University, and Dr. Pei Zhang at Carnegie Mellon University. In this work, we focus on small unmanned aerial vehicles, UAVs, that may need support during their indoor sensing tasks. These UAVs can be used to sense in areas that are difficult or dangerous for people to reach, such as in a warehouse with very high shelves or in an industrial equipment setting. The metal objects in these areas may disrupt the RF link between them and look like UAVs have been lost. This can trigger a reorganization in routing or in physical distribution of the nodes until the link is restored. To prevent this overhead, we can provide some side channel, that means some separate modality produced by the UAV itself that can indicate that it's still present, give a heartbeat to the sensing system on a whole. In order to choose the appropriate sensing modality for our side channel, we look at the limitations we might encounter during an indoor sensing task. So radio frequency RF is our preferred choice for communication and has no trouble with connectivity when there's a clear line of sight. In the same way, other modalities such as light or sound also perform best when there's a clear line of sight between the transmitter and the receiver. In the case of non-metal obstructions, RF is able to penetrate through, for example, the walls of a wooden frame building, or diffract through hallways and doorways. You can think of how you're able to use a Wi-Fi router when you're on the opposite side of a wall in a home. Light, however, is unable to penetrate through obstructions, and so connectivity will be lost whenever an obstruction exists between two UAVs. Sound is able to penetrate through thin obstructions, but mostly diffracts around and obstructions in order to still maintain connectivity. With metal obstructions present, RF is reflected and scattered, and light is still unable to penetrate, but sound can still diffract around obstructions, meaning this gives us the best chance of maintaining connectivity. The primary challenge of using sound as our side channel modality is the self-interference caused by the sound coming from the UAV itself. A flying UAV produces a high amplitude of sound coming from a combination of motor noise and propeller noise. In this figure, I show the sound frequency content of a UAV as it turns on its motors, spins the propellers for a short time, and then turns off. On the x-axis, we have the time, on the y-axis, the frequency, and the color shows the intensity of that frequency component at each time, with yellow being the most intense and blue being the least intense. The propeller noise dominates the spectrum and is spread throughout the entire signal. It's caused by turbulent air flowing over the propellers. The motor component is a lot narrow in spectrum and is caused by the vibration of the casing of the motor and its coils, together with some small vibrations of the UAV frame itself. Because this motor and propeller combined noise is so large, it's difficult to overcome it with a separate speaker. But is there a way that we can use this noise as the carrier for our sound-based messaging information? If we want to use the motor and propeller sound in some way, it means we need to modulate some parameter of the motor while the UAV is in flight. Of course, we don't want to change the controllability of the UAV. We don't want to cause a crash. So we need to investigate what parameters of the motor can be changed without affecting its controllability. To figure out how we can change the motor sound without losing controllability of the UAV, we look at the parameters of the motors that are driving the UAV. The small UAVs use pulse width modulation or PWM-driven motors, where the PWM signal has a frequency and a duty cycle. In this figure, I have 3 different PWM signals that could be used to drive a motor. On the y-axis, we have the voltage, both of the driving signal in blue and in the red, the effective voltage delivered to the motors. On the x-axis, we have the time. In the first figure at the top, the duty cycle is 20%, meaning that 20% of the total period of the driving signal is spent at a high voltage, and this results in an effective voltage about 20% of the maximum. In the middle figure, the PWM duty cycle is 90%, meaning that 90% of the time is spent at a high voltage, and the effective voltage is 90% of the maximum voltage output. In the final figure at the bottom, the period is much longer, and the pulse width of this one is 20%, as it was in the first figure. So even though the frequency has changed, the effective voltage delivered to the motors is about 20%, just as it was in the first figure. The last figure is exaggerated to show that as you decrease the frequency, as the period becomes longer and longer, we introduce fluctuations into the effective voltage. So the important thing is that while we can change the frequency, we must not drop it too low so we don't introduce a lot of jitter and fluctuation in the output power. So we've addressed how we can change the motor parameters without losing controllability. The second thing to address is the fact that the propeller-based part of the sound is dominating the total motor-propeller noise combination. So we need to find the shape of the motor signal or the pattern of transmission that can be detected easily in noise and convey information about the status or about which UAV is signaling. In order to select the best shape for our motor-produced signals, we look again at the frequency content of the motor and propeller noise together. So in this figure, we have 3 instances of a small UAV turning on the motors, spinning the propellers, and turning back off. The driving PWM frequency is changed for each of these instances from 5 kHz at the left to 10 kHz in the middle and 20 kHz at the right. We can see that the propeller noise is very intense at low frequencies, almost drowning out the 5 kHz component on the left, meaning we want to put most of our information content into higher frequencies. The other distinctive thing about these signals is that there are harmonics or multiples of the driving frequencies present throughout the whole spectrum. What this means is that if UAVs are transmitting at different frequencies, they will collide with messages from other UAVs at different frequencies close to their harmonics. And even when a very high frequency is chosen, the harmonics are still present, just aliased to a lower frequency, as shown on the right in the case of 20 kHz. To reduce the effect of these harmonics in the output signal, we instead use linear chirps as our motor signal. So a linear chirp means a signal where the frequency content changes from one frequency to another linearly over time. And a chirp can be characterized by its center frequency, indicating where in the frequency spectrum it lies, the length in time that it lasts, and its slope, how quickly the frequency is increasing or decreasing. In this figure, a UAV turns on its motors and then transmits an up chirp, meaning the frequency is increasing over time. We can see that harmonics are still present. However, the slope of the harmonics is multiplied in the same way the frequency of the signal is also multiplied in the harmonics. This means that by choosing a specific slope, we're able to distinguish a true signal from the harmonics that might be produced from another UAV transmitting at another frequency. Since we've selected linear chirps as our method for transmitting information, we now need a method that will accurately detect them in the high motor propeller noise background. A typical choice for detecting a known signal in a mixture of signals is cross-correlation. But in the case of these motor-produced chirps, cross-correlation is not the most effective solution. To see this, on this slide, we have the time frequency content of a signal before and after cross-correlation. This signal represents how a motor approximates a chirp by changing the PWM frequency between two values over small intervals of time. With this non-ideal step-like shape, cross-correlation doesn't lead to a nice sharp peak that we would expect with an ideal chirp. Instead, it's very spread out in both time and frequency and is hard to detect without noise, let alone in the presence of propeller noise. Instead, we use a technique known as chirp multiplication, similar to what is done in low-power protocols such as LoRa or in frequency-modulated chirp radar. So in this case, instead of producing a time domain signal that indicates clearly a chirp has occurred, we look at a frequency domain signal. And as you can see, after the chirp multiplication, we get a sharp high peak indicating the presence of a chirp, and it's located at the center frequency of the chirp. Another advantage of using chirp multiplication for our chirp detection is that we are able to separate simultaneous chirps occurring at different center frequencies, as well as distinguish between an up chirp and a down chirp. To see this, we use an ideal situation with linear chirps embedded in white Gaussian noise. On the right-hand side at the top, we have the Fourier transform and the time frequency spectrogram for these three ideal chirps, where the top two chirps in terms of frequency are down chirps decreasing over time, whereas the bottom chirp is increasing in frequency over time. Of course, the positive and negative frequency components of this signal shows asymmetry as we're looking at a real valued signal. However, after multiplication with a complex chirp, we get the figures at the bottom, where the frequency content of the chirps is split between the positive and negative frequency components, depending on whether they were up chirps or down chirps. So we can see the two high frequency down chirps appear in the upper part of the frequency spectrum, while the single low frequency up chirp appears in the lower negative part of the frequency spectrum. This means that a single pass of chirp multiplication can identify multiple chirps and decode the difference between an up chirp or a down chirp sent in a chirp signaling message. Now that we've chosen the messaging signal shape, we need to ensure that this type of message can be detected and decoded by the small UAV given their limited memory and processing power. By using chirp multiplication rather than cross-correlation, we are in fact able to perform the detection and decoding in a small UAV. The full details are present in the paper, but just to give an overview, to do cross-correlation would require not only a template that is the full length of the chirp to be matched, but also retaining audio windows of about the same length as that chirp, whereas chirp multiplication can be done with a smaller sliding window. This is significant because the Crazy Fly nano quadcopters that we use for evaluation can only support about 85 milliseconds of audio signal with their native digital signal processing support. And this is assuming a sampling rate of 48 kilohertz. This size of audio window is too small for a chirp for cross-correlation, but we can compound these windows over multiple audio samples and check for a longer chirp using chirp multiplication. At the end. So given that we had these three challenges, we now need to evaluate how well our system performs. The first challenge, we need to determine if the UAV still flies while it transmits chirps. The second challenge is to determine if these motor messages that we send using chirps are able to be decoded correctly, whether we have a single UAV transmitting or multiple at the same time. And the third challenge, which we won't go into here, but which is evaluated in the paper, is if the detection algorithm can run on the UAV with good accuracy. So the short answer is yes, it can, and please see the paper for more details. Evaluate if controllability is maintained. We use a camera and a tracking marker to track the location of the UAV in space and ask it to hover in one place with and without the chirp transmissions. So in this video, the drone starts hovering without any transmission, begins chirping, and then continues hovering after the transmission. It's still able to maintain hovering in place, even though the motor frequency is being changed to produce this chirp. When we look more closely at the displacement of the UAV, how much it drifts from that set point, we note that the displacement from the set point does increase slightly during the chirps as opposed to when there is no chirp. But what we can also see is the variation that happens during the chirp stays well within the range without the chirp, meaning that any error estimates that you have on the position of the UAV are still maintained during the chirp. Another important thing to note is we didn't change the PID controller in any way to adapt to these signals. It was able to recover with its normal functioning. To evaluate the message decoding accuracy, we place 1 to 4 small UAVs at different distances from a microphone, where all of the UAVs had their propellers on through the entire evaluation, whether or not they were actually transmitting. Each UAV was assigned its own center frequency so that we could determine which drones were sending messages at what time, and if those messages were being detected and decoded correctly. So on the right-hand side, we have a graph of the error rate on the y-axis for distinguishing between up chirp, down chirp, and no chirp. And on the x-axis, we have different distances between a single UAV and the transmitter. So we repeated this test with different duty cycles to see what the effect of duty cycle on accuracy would be, where the duty cycle ranged from 10% to 75%. So to give some context, 50% is about the level of the duty cycle for the UAV to hover normally. And we note that we have almost perfect decoding accuracy with 50% duty cycle and a single UAV at up to 4 meters. If we look at the more extreme values of duty cycle, 10% or 75%, we notice that the behavior is much less reliable. And this is due to the changes in the frequency content of the PWM-driven signal as the duty cycle changes. So besides evaluating a single UAV transmitting at different distances, we also evaluate the accuracy when 2, 3, or 4 UAVs are transmitting with different distances to the receiver. So on the left-hand side, we see the frequency content of the audio signal when there are 4 UAVs transmitting at the same time. And on the right-hand side, we see the accuracy, which is 1 minus the error rate, the accuracy as the distance to the receiver increases. So the important thing to note is up to 1 meter, we have nearly perfect accuracy. And even after that, we're able to attain good accuracy for multiple UAVs transmitting at the same time. So in conclusion, we've presented a sound-based heartbeat system for small UAVs, where we use the modulation of the motor to generate a sound that can be detected through the high-amplitude propeller noise. Even though we change the motor behavior during flight, we're able to maintain controllability of the UAVs and we're able to have up to 4 UAVs at the same time, separated and the messages decoded within the memory limits of the small UAVs. So I hope you enjoyed this talk, and I welcome any questions that you may have. If you'd like to get in touch afterwards, my email address is available here. Thank you.